Hello everyone, I'm Amar Dhamdhere, and I'm a product manager in the VM sizes team in Azure Compute, the team responsible for delivering our optimized and Cobalt VM portfolio. Put simply, when a customer picks the right VM for the right workload at the right price, that is our team's job. Today, I want to talk about the work I'm proudest of, Cobalt. It is Azure's own silicon purpose-built for the cloud, and it is reshaping the price-performance conversation for our customers. The customer excitement behind Cobalt 100 has been remarkable. And what is coming next with Cobalt 200 is the most exciting roadmap I have worked on in years. So thank you for being here. Let's get into it. Here's how we'll spend the next 20 minutes together. First, I will walk you through the customer excitement and feedback we are seeing from Cobalt customers today and who are running on it and the kinds of workloads it is winning. That sets the stage for everything that follows. Second, I will introduce Cobalt 200, Azure's leading performance offering, and the new VM family taking shape around it. Third, we will go a layer deeper into workload performance. I will share our early benchmark data for Microsoft-related workloads, industry benchmarks, and agentic AI. Fourth, I will walk you through the full Cobalt 200 VMs, their lineup, and the specs. And finally, we will wrap up with deployment scenarios, supported guest operating systems, and regional availability. Everything you need a plan to roll out your workloads. We have plenty to cover, so let us dive in. In 2024, we made Azure Cobalt 100 generally available, our first ever Microsoft-designed CPU, purpose-built for the cloud, and it set a new bar for ARM64 price performance. The numbers tell the story. Up to 2x the .NET performance of our prior generation, up to 20% lower cost than comparable VMs in Azure. And for developers, this is the part that matters. It is running real production workloads at scale today. Customers, including our own Microsoft teams, are already on Cobalt, and they are seeing up to 45% better performance on real-world workloads. Because of that uplift, they need roughly 35% fewer cores and VMs to do the same amount of work. That translates directly into lower bills, smaller fleets, and a small carbon footprint. Let me show who is building on it. So here's the customer excitement we are seeing, and frankly, the demand has exceeded what we planned for. Look at the breadth of customers already in flight. Every segment that matters in modern cloud workloads is represented here. These customers are migrating production workloads and consistently reporting meaningful price performance gains in many cases, the kind of gains that change the map on their roadmap. Our first-party services, some of the largest scale workloads on the planet, including Teams, Cosmos DB, Azure SQL, and Defender, are now standardized on Cobalt 100. That is an endorsement we do not take lightly because we run our own business on it before we ever ask a customer to. So let me talk about where Cobalt VMs really shine. Digital and cloud native. This is the heart of where customers are deploying Cobalt today. Scale-out and web-tier services, microservices, containers, the engine room of modern cloud applications. Plus, developers building for Windows 11 on ARM, who use Cobalt as a native cloud target that mirrors the client experience their users will run on. So the loop from dev to deploy stays tight. And increasingly, agentic AI lives squarely in this bucket. Agent runtimes, sandboxes, vector search, retrieval pipelines, model orchestration. These are cloud native by their very nature. With Cobalt 200, we can now address agentic AI workloads with the per-core performance, density, and cost efficiency they demand. The same Cobalt VMs you build cloud-native services on today are the ones your agentic systems will run on tomorrow. Cobalt also shines in modernizing the enterprise estate. This is where customers with established workloads, most of them easily portable to ARM, can move them onto Cobalt and unlock a step change in performance and efficiency. If your workload is built on Java, Python, .NET, or Go, it ports cleanly. Open source databases, in-memory caches, data processing, and analytics engines will run beautifully here. For most teams, this is a recompile and go. The heavy lift you may be imagining is rarely there. And to make that motion as easy as possible, we have partnered deeply with ARM Holdings on migration tooling. Through Azure's own porting frameworks and the ARM partnership, the migration guides, dependency analyzers, and runtime support across the major languages are available today. So that is where Cobalt VMs shine. Cloud native and agentic AI on one side, modernizing the enterprise on the other. This is the work we did with Cobalt 100 and the work we are extending now with Cobalt 200. We started this journey with Cobalt 100, our first Microsoft-designed CPU for the cloud. The impact on external customers and our own Microsoft teams has been real, measurable, and consistent. That performance and feedback from those customers, it is what has shaped Cobalt 200. The headline result, up to 50% higher performance over Cobalt 100, and it will be Azure's leading performance offering in the market. Building on what Cobalt 100 delivered, Cobalt 200 takes the next step, a new architecture, a refined design, and a real step change in performance. And on top of that foundation, we are introducing entirely new VM families engineered to run a wide variety of workloads. Cobalt 200 is built for the workloads that define this era of cloud computing, cloud-native services, and agentic AI. These are the workloads where developers are spending most of their time today. Containerized microservices, distributed data pipelines, vector search, retrieval model orchestration, and the agent runtimes that sit on top of them. They are concurrent, they are memory aware, they are IO sensitive, and they need to be cheap to run at scale. That is exactly what we designed for. And that is why Cobalt 200 ships not as a single SKU, but with a full set of VMs, expanding our portfolio from DP, DPL, EP on Cobalt 100, to which we are adding high memory optimized VMs and dense local storage optimized VMs, with the breadth to match a VM to the workload you can actually run in Azure. Cobalt 200 runs on Azure Boost, and it is our most power efficient Azure compute offering yet. Now, this is the slide that matters most to developers, and it is the one I'm proudest of. What you are looking at is Cobalt 200 per core performance measured relative to Cobalt 100 across 3 different lenses. On the left, industry standard benchmarks, the kind of vendor neutral repeatable measurements your engineering teams already trust. Across the board, Cobalt 200 delivers a meaningful generational leap over Cobalt 100. In the middle, our own Microsoft benchmarks, broader, more diverse workload coverage, the kind that mirrors what actually runs in production environments. Same story, a clear, consistent step up. And on the right, the strongest signal of all Microsoft's own products. These are first-party services running at hyperscale on real customers' traffic every single day. When those workloads see this kind of uplift, you know it is not a synthetic number, it is real. I want you to focus on the shape of the chart, not on any one bar. Workloads are different, and your workload will land somewhere along this distribution. But the headline is consistent. Whether it is an industry benchmark, a Microsoft benchmark, or a real Microsoft product, every single bar to the right of Cobalt 100 tells the same story. Cobalt 200 raises the floor on per core performance. For developers, that means more work done per core, fewer cores to provision, lower bills, and real headroom to scale. This is where Cobalt 200 starts to matter most for the next wave of cloud workloads, the wave we are all building towards right now, agentic AI. There are 3 things that I want you to take away from this slide. First, why this matters. The industry is converging on a new way of thinking about performance for agentic workloads. It is no longer just about throughput on a single request. It is about how fast you can spin up an agent sandbox, how quickly that agent becomes responsive, and how many of them you can run concurrently on a single machine. That is the metric that translates per core performance into real product and customer value, and it is the lens we have built our benchmarks around. Second, what we are seeing on Cobalt 200, our internal agentic benchmarks. Time to interact the moment you request an agent sandbox to the moment it can start doing useful work is meaningfully faster than on Cobalt 100. Spawn rates are up. The latency story is consistent with the per core performance story we showed earlier. The platform is faster, end-to-end, and the developer experience reflects that. Third, density. Because Cobalt 200 delivers more useful work per core, you can pack more agent sandboxes onto the same VM and more agents onto the same fleet. It translates directly into lower cost per agent, higher concurrency for your end users, and real headroom as your agentic workloads scale. Per core performance translating into real product and customer value, Cobalt 200 is the platform we want you running your agentic workloads on, and the benchmarks back that up. Let's go over Azure's VM offerings that enable developers and users to bring their workloads to run on Cobalt 200. Our 2 foundational VM families, general purpose and memory optimized. These are the workhorses that have powered the bulk of custom deployments on Cobalt 100 today. and we are now refreshing them end to end on the new generation. On general purpose, you have two profiles, a DPLS and DPLDS series with 2 gigabytes of memory per vCPU, scaling from 1 up to 128 vCPUs and up to 256 gigabytes of memory, purpose-built for media encoding, gaming servers, microservices, and small databases. And a DPS and DPDS series at 4 gigabytes of memory per vCPU, also scaling up to 128 vCPUs and up to 512 gigabytes of memory, the natural home for application servers, web servers, and small to medium databases. On memory optimized, the EPS and EPDS series at 8 gigabytes of memory per vCPU, also up to 128 vCPUs and up to a terabyte of memory for the larger in-memory databases, caches, and analytics workloads. Across all of these, the platform underneath has been leveled up to 7 terabytes of NVMe local storage, up to 85 gigabits per second of network bandwidth, and up to 70 gigabits per second of remote storage throughput. And as always, you can attach standard, premium, SSD v2, and Ultra disks based on regional availability. The takeaway, the Cobalt VM families you have been deploying are still here. Same shape, same ergonomics, same workload fit, and now with a meaningful step up in performance because of Cobalt 200 underneath. This is where Cobalt 200 generation gets really interesting. These are not refreshes of existing SKUs. These are entirely new VM types, built directly in response to what customers have been asking us for. First, a new high memory profile, the MP series. This is built for workloads that need a lot of memory per core, large in-memory databases, caches, big analytics workloads, relational databases, and ERP. We have set the ratio at 16 gigabytes of memory per vCPU, scaling up to 84 vCPUs and roughly 1.3 terabytes of memory in a single VM. Customers have been asking us for this profile for years. Cobalt 200 makes it possible to deliver it at the kind of price performance the rest of the family is known for. Additionally, a brand new dense local storage profile, the LP series. This one is for customers running data preprocessing, storage caching, relational and NoSQL databases, big data analytics, and search and index engines. At 8 gigabytes of memory per vCPU, with up to 128 vCPUs and a terabyte of memory, and up to 23 terabytes of NVMe local storage sitting right next to compute. This is for storage-hungry, latency-sensitive workloads where the math fundamentally changes. Both of these additions are the clearest example of what we mean when we say Cobalt 200 was shaped by customer feedback. Each one fills a gap customers told us mattered, and each one is enabled by the new silicon and the new platform working together. On Guest OS, the short version is we support a broad set of distributions. All the major Linux families, plus Windows 11 client for our developer scenarios. Whatever your team runs today is almost certainly on the list. Make certain you are using the latest patches, kernels, and libraries to get the most performance out of the Cobalt VMs. On feature parity, Cobalt 200 supports the full set of Azure capabilities you depend on across management, security, core platform, and developer tooling. And support for newer capabilities continues to grow. One question I get a lot, do I have to learn a new way to operate ARM VMs? The answer is no. ARM-based VMs are built into Azure exactly the way our x86 VMs are, so there is no difference in how customers consume them. The same Azure control plane, the same tools, the same workflows. Everything you see on the slide, ARM, Portal, CLI, Marketplace, scale sets, Spot, Monitor, Backup, AKS, it all just works. If you know how to run a VM on Azure today, you already know how to run an ARM VM on Azure. On regions, Cobalt 200 is launching in West US 3, East US 2, Central US, and Sweden Central, and we will continue to expand regions from here. The key thing to remember is that the link at the bottom of the slide, product availability region, is the source of truth for the latest regional footprint, so please bookmark it. Before we wrap, here is a quick map of where to go next. We have collected the resources you need to start building on Cobalt today and to get ready for Cobalt 200. You will find real-world Cobalt 100 customer stories on the Azure blog, the Cobalt 200 announcement blog for deeper technical narrative, a full ARM migration overview from ARM learning paths, the ARM software ecosystem dashboard so you can confirm the libraries and runtimes your stack relies on, and the Azure Cobalt VM documentation on Microsoft. Learn for hands-on guidance. We are humbled by the developer community building alongside us and incredibly excited to see what you build next on Cobalt 200. Thank you.
Hello, everyone. I'm 𝗦𝗽𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀, Principal Product Manager on the Azure Boost team. Today, I'm excited to talk to you about the latest generation of Azure Boost, Azure's server offload technology, which has recently become generally available with the general availability of the first VMs using this technology, the Intel-based V7 VMs. I'll give an overview of what Azure Boost is and specs of this latest generation. And then I will do a deep dive on one of Azure Boost's powerful features, Guest RDMA, which allows direct memory-to-memory data transfers between VMs without involving the CPU or operating system. So let's dive in. So what is Azure Boost? Azure Boost is a Microsoft-designed system that offloads virtualization tasks traditionally handled by the hypervisor and host OS onto specialized hardware and software. This gives us the ability to optimize performance across various workloads, increased host isolation from customer virtual machines, improve servicing, allowing us to maintain the platform in the background without a visible impact to customers, improve networking performance and storage access, especially as we dive into Guest RDMA. This has multi-dimensional improvements across isolation, minimizing maintenance impact, performance, and enabling bare metal functionality. This advancement is enabling industry-leading remote storage throughput and IOPS, significantly improving performance for data-intensive and network-heavy workloads. Relative to Build 25, with the next generation of Boost, you can see dramatic increase in storage throughput, IOPS, confidential device support, increased saturation greater than 25%, and total networking bandwidth of 400 gigabytes a second. This is aiding in the advancement of confidentiality across the fleet. You can experience these new capabilities in our latest optimized V7 VM SKUs, featuring a 3x increase in networking bandwidth, 400,000 connections per second across 2 million concurrent connections. And on the remote storage front, the system can achieve up to 20 gigabytes a second of throughput and 1 million IOPS, capabilities the latest VMs will be able to support in the future. These performance gains are available on the latest versions of Azure Boost. Now let's talk about how traditional networking works today and how Azure Boost Guest RDMA changes that. With TCP, every data transfer is CPU intensive. Every single packet has to travel through the full networking stack, and along the way, you're paying for protocol overhead, context switches, and processing delays at each layer. The end result, TCP consumes a significant amount of CPU, and it introduces extra latency that's hard to avoid. Now let's look at how this changes with Guest RDMA. Guest RDMA allows direct access to memory. It bypasses the operating system layers and removes all of those intermediate steps in the networking stack. So instead of data moving through the TCP/IP layers, it's transferred directly between application memory and the network interface. And the impact of that is significantly lower latency and dramatically reduced CPU overhead. Now to talk about RDMA and why it matters for network application developers. At its core, RDMA gives you an alternative path, one that's far less CPU intensive than traditional networking. Things you'd normally handle in software message packetization and reassembly, reliability, flow control, congestion control, and all of that gets offloaded to the NIC. That means your applications can bypass the traditional networking overhead entirely. And the result is a significant reduction in both latency and jitter because the heavy lifting moves out of software and into hardware. This becomes especially important for workloads that demand both high bandwidth and very consistent latency. Think large-scale AI training distributed inference and HPC workloads. These are scenarios where every microsecond counts. With RDMA, we can push up to 200 gigabits per second of throughput on a single connection while still holding onto very tight, predictable latency characteristics. Now on Azure, we take this a step further with RDMA network virtualization. What this means is RDMA traffic now works seamlessly inside the cloud-native constructs you already know and use in virtual networks. So you don't have to choose between RDMA performance and the cloud-native features that your architecture depends on. You get both. And this capability is available today on Azure Boost instances through the Microsoft Azure Network Adapter, which brings high performance and full virtualization support together in one place. So with that foundation in mind, let's look at how this actually shows up in a real workload. On the next slide, you'll see a distributed inference example, and that's exactly what we'll be demonstrating live in just a moment. This demo shows the impact of RDMA for distributed AI inference by directly comparing resource utilization across the two transport paths, TCP and RDMA. In this setup, we disaggregate the inference pipeline into two stages, prefill and decode, so they can run on separate resources and scale independently. We're running a disaggregated inference workload across two VMs on the same Azure ND GB200 v6 cluster, once over TCP and once over RDMA. We're running the 𝗦𝗲𝗀𝗶𝗸𝗁 70 billion instruct model using the VLLM benchmarking tools, specifically VLLM bench serve with synthetic prompt generation to drive consistent, repeatable inference traffic. These two VMs, prefill and decoder, are configured exactly like a typical inference backend for AI prompt processing. VM1, the prefill VM on the left, this is the VM that processes the user's input prompts. It builds up context in memory for token generation creating, what we call the KV cache, focused on prompt processing. VM2, the decoder VM, this is the memory-intensive VM. It takes the context generated by the prefill VM and it uses it to generate tokens producing the actual response to the chat prompt. The GPU here drives the inferencing engine and the results are streamed back to the client in real time. In this disaggregated architecture, the choice of transport, TCP versus RDMA, really starts to matter. This benchmark window is where we collect all of our performance metrics. We're focusing on three key metrics. First, throughput. How many tokens the system can generate per second. Second, time to first token, or TTFT. How quickly users see that very first response. And third, time per output token, or TPOT. How efficiently tokens are generated after the first one lands. And together, these three metrics give us a complete picture of how RDMA changes the performance profile of distributed inference. Let me walk you through the demo screens. On the left side of the screen, the top window is the prefill VM, and the bottom window is the decoder VM, the same two VM setup we just walked through. On the right, we have two views. At the top, you'll see the benchmark results as they come in. And at the bottom right, we have the RDMA stats. These light up and update in real time whenever RDMA traffic is flowing. So when RDMA is enabled, you'll see those counters actively ticking. That's your visual confirmation that the data path is going through the RDMA fabric, not TCP. And the demo has two runs, one after another, on the same inferencing workload. In the first run, the transport is TCP. In the second run, the transport is RDMA. This gives us an apples-to-apples comparison, same model, same prompts, same VMs, only the transport path changes. Now, when we compare the results in the benchmark window across the two runs, RDMA versus TCP, we see clear, measurable improvements across all three of our key metrics, up to 2.2 times higher throughput, a 3 times reduction in time to first token, and about 20 to 25% faster token generation after that first response lands. So across the board, throughput, responsiveness, and per token efficiency, RDMA delivers a meaningful step change in performance for distributed AI inference on Azure. We're excited to share that the preview program kicks off in June 2026. This will start as a limited preview so we can work closely with early customers and make sure the experience is rock solid before we open it up more broadly. If you'd like to be part of it, please fill out the sign-up form to join the program, and we'd love to have you on board. To conclude, we have collected resources for you to learn more about Azure Boost and its unique features. Here you will find blog posts and documentation that explain more about our technology. We are excited about this latest technology and look forward to the developer community building and creating their newest cloud services on these VMs. Thank you for watching.
Hello everyone, I'm Amar Dhamdhere, and I'm a product manager in the VM sizes team in Azure Compute, the team responsible for delivering our optimized and Cobalt VM portfolio. Today I'll talk to you about several recently announced Intel and AMD based general compute VMs, both generally available and in preview. Let's begin with the new Intel VMs, beginning with the general availability of DSV7 and ESV7 series VMs. We are excited about the Intel DSV7 and ESV7 series VMs, which have recently been made generally available. These are the VMs that are bringing the performance benefits of the latest generation of Azure Boost to our customers and are based on the Intel 6th generation Xeon 6 Granite Rapids processor. We see up to 15% CPU performance improvements over the previous generation. Support for very large configurations up to 372 vCPUs and 2.8 terabytes of memory and turbo frequencies of up to 4.2 gigahertz. And thanks to running on servers with the latest generation of Azure Boost, we are also seeing up to 400 gigabits per second of networking bandwidth, up to 800K IOPS and 20 gigabytes per second throughput to premium V2 and ultra-disk remote storage, and up to 9.6 million IOPS and 53 gigabytes throughput to local NVMe temp disk. Across workloads, we are seeing consistent and meaningful gains compared to the previous generation Intel VMs. CPU performance improves by up to 13%, in-memory cache workloads by up to 18%, and cryptography workloads by up to 20%. For more specialized scenarios, such as AI preprocessing and video encoding, improvements range from up to 18% and up to 24% respectively. Here we talk about the Intel Network Optimized VM series, purpose-built for high-performance NVA workloads. These VMs deliver storage price performance with up to 4 vNICs available at smaller 2 vCPU sizes and scaling up to 15 vNICs on larger configurations. For workloads with high connection churn, larger sizes can support up to 400K connections per second, making them ideal for demanding network appliances. At the top end, the 128 vCPU VM sizes enable up to 200 gigabits per second bandwidth with significantly higher bandwidth ceilings across all sizes compared to general purpose VMs. This combination of high connections per second, flexible vNIC scaling, and elevated bandwidth makes the series well suited for firewalls, gateways, and other packet processing workloads. For remote storage intensive workloads like databases and analytics types, we've introduced the EBSV6 series. These VMs run on the Intel Emerald Rapid CPU. The key highlight here is not just CPU improvements, but the integration with the Azure Boost, which enables scale remote storage throughput and IOPS significantly higher than general purpose VMs. The charts show the max throughput and IOPS on these VMs, up to 14 gigabytes per second and 800,000 IOPS respectively. Here are Azure's AMD-based DA, EA, and FASV7 VMs. These cover general purpose memory optimized and compute optimized workloads and have options with and without local SSD. They also include new constrained core sizes for better cost control. The new AMD VMs are powered by 5th generation AMD EPYC Turin processors, delivering up to 35% CPU performance improvement over the prior generation. They scale up to 160 vCPUs and 1.25 terabytes of memory and supporting boost frequencies up to 4.5 gigahertz. These VMs already live in 11 regions with broader expansion planned in 2026. This slide focuses on gen-over-gen performance improvements for AMD V7 VMs compared to V6 across a representative set of benchmarks. The blue bars represent V6 and the pink bars represent V7. The key takeaway is that AMD V7 provides material performance gains and vary by workloads. We are seeing up to 35% improvements in CPU performance, up to 25% for Java-based workloads, and up to 65% for in-memory caching, and up to 80% for crypto workloads, up to 130% on web applications. Now let's talk about our new AMD-based LASV5 VMs optimized for local storage-intensive workloads. For these storage-intensive scenarios like caching layers and search that benefit from local NVMe storage, LASV5 VMs is the latest of our AMD-based offerings. These VMs run on 5th generation AMD EPYC Turin processors and offer up to 35% CPU gains and increased total local disk capacity and IOPS. We are maintaining consistent ratios on disk to vCore while also expanding to larger sizes. For even more local storage-intensive scenarios like big data processing, the LAOSV5 is our latest AMD-based dense local storage optimized VM series with 3x the local storage ratio as that of the LASV5 VMs. These VMs offer significant increases in maximum local disk capacity and IOPS compared to the previous generation of LAOSV4 VMs. Before we wrap, here is a quick map of where to go next. We have collected the resources for you to learn more about these Intel and AMD VMs. This includes blogs for all of the VM series we discussed today. We are excited by the release of these new VM series and hope they will match up well for the various general compute workloads you plan to build on Azure. Thank you for watching.
Hello everyone, I'm 𝗦𝗽𝗲𝗸𝗀𝗀𝗐𝗔, Head of Product for Azure Compute Security and Confidential Computing. Today, I'll be discussing how Azure secures compute on our servers and the VMs and containers that run on these servers. I'll discuss how we enhance VM security on select VMs using confidential computing, how we have innovated with live migration for confidential VMs, and finally, I'll discuss the general availability of the latest compute security innovation, Azure Integrated HSM. So let's get started. A secure hardware system architecture is not a single security layer of defense, but it's rather a series of security technologies applied at every layer of the stack. The most effective security solution is constructed upon a solid foundation, and anchoring security in hardware forms that foundation. The layers of Azure hardware system security architecture are built on these following distinct technologies. The first is the innovation that we've done with confidential computing, a silicon root of trust, leveraging Azure Boost, our secure host hardware management infrastructure, and finally the innovations that we've done with Azure Integrated HSM to meet the FIPS 140-3 Level 3 standards. While I won't have time to focus on all of these, we'll focus on just a few and see how far we get. The next layer of defense is the compute that runs on your virtual machines and containers and services across the cloud environment. Typically, there's inconsistent isolation between tenants and cloud providers. We have done a ton of work in Azure to ensure that the tenants themselves are isolated from each other and the tenants are isolated from the cloud provider. So we have security engineered into the platform, ready to protect every workload. So as I mentioned earlier, we ensure that tenants are isolated from each other. So we provide capabilities such as trusted launch, disk encryption capabilities, various key management offerings, verified boot chains, controls with Azure Kubernetes service, and just-in-time memory access. In addition to tenants doing the work to protect themselves, we also ensure that the cloud provider Azure is isolated from the tenant workloads. Our investments in Azure Boost lead the way. The work that we're doing with Azure Integrated HSM, with confidential computing, the Calyptra root of trust. These are just some parts of the assets that we've put in Azure to ensure that the cloud provider is isolated from your workloads. So while we work on isolating your workloads, I wanted to talk a little bit about confidential computing. So our industry has had encryption of data at rest and in transit for quite a long time. But protecting that data when it is in use in memory has not yet been solved at scale by our industry until now. What we've done with confidential computing is we protect that data when it's in memory, when it is in use, from outside that trusted boundary that we call the TEE, which is a trusted execution environment. A TEE provides assurance of data and code integrity as well as data confidentiality. So confidential computing, in the end, is an ability to protect your data when it is in use from malicious actors and malicious code. That's the first important takeaway. The second important takeaway is now that we have confidential computing, your data and code are protected during its entire life cycle from the time it starts, it's created, to until it is destroyed, with a confidential key that you own. Next, I'm going to talk about the innovations that we've done with our V6 confidential VMs built on AMD's SEV SNP technology. AMD SEV SNP provides hardware-enforced memory encryption, protecting data in use from the host, the hypervisor, and the other tenants. The strong isolation model ensures both memory and CPU state remain private, even from privileged infrastructure layers. The built-in attestation capability provided by our Microsoft Azure Attestation Service or using in-guest attestation, customers can verify the VM integrity before releasing secrets or operating on sensitive workloads. AMD SCV/SNP V6 confidential VMs support enterprise-scale workloads with high core counts, memory, and make them practical for real production deployments. We also have integrated with Kubernetes, cloud-native tooling, and enable secure containerized workloads without architecture. The improved performance compared to previous generations reduces the additional trade-off that you might have to do between security and efficiency. In fact, with AMD SCV/SNP, we have moved our security-critical workloads, such as Entra ID, to run entirely on confidential computing. Next, I will talk about Intel TDX with our V6 confidential VMs. Intel TDX, like AMD SCV/SNP, extends confidential computing to a broader set of workloads with strong VM-level isolation using TDs or trusted domains. OpenHCL, which is our paravisor, supports increased transparency and trust by enabling more visibility into the firmware stack. High-performance configurations with large vCPU and memory support make it suitable for data-intensive and enterprise workloads. And new capabilities such as accelerated storage and infrastructure improvements will help close the performance gaps that reduce the asterisks when operating with confidential VMs. These enable customers to lift and shift their sensitive workloads into Azure without exposing data to the cloud operator. And coming soon, we will be bringing confidential VM live migration to Intel TDX. Live migration on confidential VMs will provide near zero downtime for maintenance and upgrades. These eliminate outages and avoid operational disruption for mission-critical workloads. These also improve reliability and performance by transparently moving workloads away from failures and rebalancing capacity without requiring customer intervention. Next, I'll show you a demo.
In this demonstration, we show confidential live migration. We have two servers. The left is the source and the right is the destination. Up top, I've RDP'd into the CVM running on the source, and we're running a basic script that's printing hello and the time. On the destination machine, we're showing attestation and key exchange occurring. Here you can see the live migration is progressing, key exchange is complete, and the handoff is occurring. The system has now moved the CVM from source to destination, and we can see here the time continues to print with just a short blackout time.
Now I'm excited to talk about Azure Integrated HSM. AI HSM is our first-party security ASIC that acts as a secure hardware-backed node local key vault. Customers can use this to offload the keys that they typically store in Azure Key Vault, Azure Managed HSM, or even an external key manager. With Azure Integrated HSM, customer keys are never exposed in the clear, and keys remain in the AI HSM boundary while in use without any performance penalties. They also benefit from compliance and testing because we have FIPS Level 3 140-3 certification on these devices. So the key difference here is that the keys no longer need to sit in the VM memory in clear text. With AI HSM, crypto operations are offloaded to a local PCIe SRIOV device on the node, thus enabling the keys to remain inside the HSM boundary. And the VM uses a local interface to access them securely as shown in the diagram. This reduces exposure to memory-based attacks while also improving performance compared with repeated remote HSM calls. Now, practically, this changes the threat model. For example, even in cases like crash dumps or memory inspection, sensitive material is not exposed because it never leaves the HSM boundary. At the same time, because the interface is local to the VM, customers get lower latency, higher throughput for cryptographic operations, making this viable for high-scale production workloads without forcing a trade-off between security and performance. So in conclusion, building verifiable trust, rooted in hardware, enables organizations to develop new applications and easily migrate their existing applications that contain data that must be protected at all times. We have prepared this list of resources on compute security and confidential computing to help you learn more and start using these technologies to enhance the security posture of your workloads on Azure. We look forward to help you bring your most sensitive workloads and data to Azure. Thank you.